We'll practice calculating electron speed and the Broglie wavelength in the Davisson-Germer experiment. Here's the problem. In the Davisson-Germer experiment, electrons are accelerated through a potential difference of 54 volts and diffract off a crystal, demonstrating the wave nature of matter. Given the charge of an electron as 1.6 times 10 to the negative 19 coulombs, the mass of an electron as 9.11 times 10 to the negative 31 kilograms, and Planck's constant as 6.63 times 10 to the negative 34 joule seconds. Part A. Find the speed of the electrons. Part B. Find their de Broglie wavelength, and state why diffraction is observable. First, find the kinetic energy gained by the electrons. The kinetic energy equals the charge times the potential difference. Kinetic energy equals E times V, which is 1.6 times 10 to the negative 19 times 54, giving 8.64 times 10 to the negative 18 joules. Now use the kinetic energy to find the speed. Since kinetic energy equals 1/2 mv squared, solve for V. V equals the square root of 2 times ke over m, which is the square root of 2 times 8.64 times 10 to the negative 18 divided by 9.11 times 10 to the negative 31, given the square root of 1.90 times 10 to the 13, which is 4.36 times 10 to the 6 meters per second. Next, find the de Broglie wavelength using lambda equals h over mv. Lambda equals h over mv, which is 6.63 times 10 to the negative 34 divided by the product of 9.11 times 10 to the negative 31 and 4.36 times 10 to the 6, giving 6.63 times 10 to the negative 34 divided by 3.97 times 10 to the negative 24, which equals 1.67 times 10 to the negative 10 meters. Interpret the result. Lambda is approximately 0.17 nanometers, which is comparable to atomic spacings in a crystal, so the electrons diffract, direct evidence of the wave nature of matter. Remember, the de Broglie wavelength of a particle is h over momentum, and diffraction occurs when the wavelength is on the order of atomic spacings.